One of the first applications that we're going to talk about when it comes to what a derivative is a motion application. And we think about rate of change, which we use to reference slope. Rate of change can also be used to reference an object's motion. So if we think about velocity as being something's rate of change, if you think back to just really basic math, basic physics, average velocity is how far did you travel and how long did it take? And that's what this is. Your S, for some reason, S is used a lot for position. So it's taking your difference in your position divided by your difference in time. So maybe you traveled 500 miles and it took you 7 hours. So to figure out your average velocity, you're just going to strictly divide. Well, then we have what's called instantaneous velocity. Instantaneous velocity is not an average, it's a velocity at an exact moment, just like slope is looking at an exact spot on a graph. And if you look at the formula for instantaneous velocity, what you're going to notice is it looks a whole lot like what we just did for that derivative with the limit definition. It's your limit as your time change is going to zero of the position of s plus the change in time minus s of t all over delta t. And if you just think of all of your delta t's as being the same as your h's, this is your derivative. So what that tells us is the velocity of a function is just its first derivative. So if I derive it, I should get velocity. So we would consider position. Again, a lot of times position is either x or s. And then when you derive position, you get velocity. So let me show you how this works in an actual motion question. So if you think back to like basic position or function that you would use in like algebra, algebra 2 to talk about like parabolic motion, we have this formula that utilizes like how something moves with respect to gravity. And the formula is -1/2 gt squared plus v sub o t plus s sub o. So g is your acceleration due to gravity. We are either going to use 9.8 if it's in meters per second or 32 if it's in feet per second. Your v sub o is your initial velocity. So when you start, what is the velocity of whatever is moving? And then your s sub o is your initial position or your initial height. So if we have a formula written like this, well, that's a position function. First of all, I know that because it's a -16, I must be working in feet. Your 16t tells me my initial velocity is 16 feet per second. And then your 32 at the end tells me the initial height of this object. In this case, it's a car that's flying over a bridge. And so when the car flies over the bridge, starts at a height of 32, and you can kind of picture it like going down into like a parabola. And we want to know two things. We want to know when will the car actually hit the water, and then we want to know what would the velocity be at that time. Now, the first question is not a calculus question, it's an algebra question. When it hits the water is when does it have a height or position of 0? So this first part wants to just find the 0 of this polynomial. Now, I purposely picked one that you would not need to grab a calculator. You can factor out a -16, which gives you t squared minus t minus 2, and that factors t minus 2, t minus 1, t minus 2, t plus 1. Sorry about that. So my two t values that make that equal to 0 are 2 and -1. Well, t is representing time. And one thing we know about time, it can't be negative. So this -1 answer makes absolutely no sense because we're not traveling back in time. So that tells me is after 2 seconds the car would hit the water, the height of the water would enter the water. So then part B is actually the calculus part. Now that we know that it takes 2 seconds to hit the water, what is the velocity at that time? So what you're going to do is you're going to derive this position function. We're going to call it v of t, or velocity at time. So the derivative, power out front, power 1 less. Derivative of 16t is just 16, and the derivative of 32 is 0. Now we can find the velocity at any time just by plugging that time in for t. So I want to know the velocity at 2. And again, this one probably don't need a calculator. So you get -64 plus 16, which is -48. Velocity, in this case, this is feet per second. So let's talk about the negative for a second. It should not surprise you that it's negative because velocity has a direction. And what this negative is telling me is that it is heading downwards. And it is also telling me that it's getting closer to the water. So the reason that that is negative, it should be negative, is because of the direction the car is moving. So when we talk about derivatives and kind of what they do, we actually can take what's called a higher order derivative. So if you're going to see a section on Delta Math that talks about higher order derivatives. Higher order derivatives simply means taking more than one derivative. So everything we've done to this point, I think I referred in the last slide to the first derivative, means you did this process once. You can repeat the derivative process over and over and over again. Now, some of the derivatives have a ton of applications. Some are just doing it just for the sake of doing it. So if you have your original function as f of x, so that's your original function. If it's a motion question, this original function would be your position. So if you're talking something that is moving. If you derive it once, we use this notation, we use this notation, we use this notation. These are the three most common notations for a first derivative. So using a prime symbol, f prime or y prime, or using dy dx, that's your first derivative. And if it's a motion question, it would be velocity equation. If you derive again, here there's lots of ways to write this. You can use two prime symbols. So you can do f double prime or you can do y double prime. The longer way to write this is d squared y over dx squared. It means you're deriving y twice in terms of x. All of these things mean second derivative. Second derivative has a lot of applications, some of which we'll look at this chapter, some of which we'll wait till next chapter. As far as motion, and I'm hoping you're sitting there going, okay, well, I think I've taken a little bit of physics. I know what comes next. The application for this is it represents an acceleration equation. So it will tell us my acceleration at a particular time if I derive the position twice. After that, the usage is not as common. So you can do three prime symbols. This is a third derivative. There is a version with this d1. It's d cubed y over dx cubed, although I feel like that doesn't get used very much. But that is my third derivative. It does not have any motion applications. Once you get past a third derivative, we stop doing prime symbols because they start to all run together and then you're not sure what's going on. So instead of that, you'll start to see the derivative put in parentheses. So you'll see it written like that, or you'll see it written like this. That's your fourth derivative. And then same thing beyond that. If you want to derive it again, that's your fifth derivative. So the idea is you can continue the derivative process over and over and over again and get higher and higher derivatives. But truly, after you derive twice, you lose a lot of its application. And polynomials are the absolute easiest to derive many times. So let's do 7x to the fourth plus 3x to the third plus 2x minus 5. So my first derivative, just power out front, power 1 less, power out front, power 1 less. And then my second derivative gets a little easier. You will end up have some bigger coefficients though. So you got to do 3 times 28. What is that? 84 x squared plus 18x. Derivative 2 is 0. And then I can go 3 derivatives. And so that would be 168x plus 18. And then I could go 4 derivatives. Oh, come on, it doesn't want to write down there. 4 derivatives is just 168. And then I could do a fifth derivative, which is 0, and then everything after that would be 0. So polynomials, you can derive a lot of things multiple times, but polynomials are by far the easiest to derive over and over and over again because you see them get simpler and simpler as the powers drop down. So that's just a basic idea of how you take a derivative more than once.